Okay, I'm going to continue now with some more examples of how to classify isolated singularities, but this time I'll do some slightly harder ones. So, the first one I've written here, I've written out a function f, and I want to classify the singularities. Now, so first I have to figure out where these singularities are, and that's going to be when the denominator is 0. So I guess first thing I should do, I should factorize the denominator fully to see where those points are. So this is equal to sine cubed z on z cubed z squared plus 4. That can be written as a difference of two squares. So you can factorize it like this. Z minus I, z plus 2i. And then you have z plus 4 all squared. So it's easier to see then that singularities occur at, well, it's going to be z equals 0 plus or minus 2i and minus 4. Okay, that's the first thing. Now, it's not too hard to see that plus or minus 2i and negative 4 are just going to be poles. If you just use the same argument I used in the previous video, it should be easy to verify that. So you should find that negative 4 is a pole of order 2. And plus or minus 2i are simple poles. Should be fairly easy to see that when you try it. Z equals 0 though is different. You might think that z equals 0 is a pole of order 3. Let's see why that's not true. Because if I try to write f of z as being g of z on z cubed, then I would have to take g of z to equal sine cubed z on z squared plus 4, z plus 4 squared. And although this is analytic near z equals 0, the only place where it's not analytic is at negative 4 and plus or minus 2i. So it's definitely analytic near z equals 0, but unfortunately g of 0 does not is non it's not non-zero. It's equal to 0, right? So that definition falls apart. So z equals 0 is not a pole of order 3. So in that case, it must either be removable or essential. So we can, to check it's removable, remember what you can do. You can check to see if this limit is equal to 0. If it is, then you know it's removable. That's an equivalent definition for a removable singularity. So let's see. This becomes limit as z approaches 0 of sine cubed z on z squared plus 4 times z plus 4 all squared. I can split this limit up. I can write this as the limit as z approaches 0 of 1 on z squared plus 4 z plus 4 squared times the limit as z approaches 0 of sine cubed z on z squared. Right? Now, the limit on the left, that function on the left is well defined at 0, so I can just sub in z equals 0, and you can see that that limit is going to be 1 on 16. The right, though, is not so easy, because the top and bottom are both approaching 0, but that means I can apply L'Hopital's rule, right? So this is going to be 1 on 16 times the limit as z approaches 0. And if I differentiate top and bottom, I get 3 sine squared z cos z over 2z. Again, I can bring the 3 out and the 2 out, so it's 3 on 32. I can split this limit up once more, bring the cos z out, and write it like this. Yeah? So now, as z is approaching 0, cos z I know just equals 1. But again, this guy here, top and bottom are approaching 0. But again, I can just use L'Hopital's rule one more time. So this is going to equal limit as z approaches 0 of 2 sine z cos z on 1. And now this is well defined at 0, and it just equals 0. So this entire limit equals 0. So it follows by that alternative definition that therefore z equals 0 is a removable singularity. That's how you would answer that particular question. So it's a bit of a harder one, but still not, as you can see, it's not that difficult. Let's have a look at another slightly harder one. Okay, so example number 2. I'm going to classify the singularities of the following function. Z squared minus 9, z plus 2 cubed. Okay, so first of all, where are the singularities? Well, in other words, where is this function undefined? I know that this function is undefined when the denominator is equal to 0. And that's going to occur at -1 plus or minus 3 when z squared equals 9, or -2. But that's not all. If you see, I also have e to the power of 1 on z on the numerator, and that guy is undefined at z equals 0. So z equals 0 is also an isolated singularity. Okay? Now, when it comes to plus or minus 3, again, it should be fairly easy to see when you try it that plus or minus 3, they're just simple poles. Right? That part's not too hard. And z equals minus 2 is a triple pole. That's not very hard to show either. Just write f as some function. Find a function g such that f can be written as g on z plus 2 cubed. When you do that, you should find g is analytically a -2 and g is non-zero at -2. So by definition, it's a triple pole. The singularities I want to focus on are the singularities at -1 and 0. You may think that -1 is a simple pole because it appears on the denominator once as a factor. But again, notice I have a sine squared z plus 1, which is going to equal 0 when you put z equals -1. So if you try that argument, you should find it breaks down. So you should find that z equals -1 can't be a simple pole, meaning that it's either removable or essential. So let's check if it's removable. Again, if I want, I could check to see if limit as z approaches negative 1 of z plus 1 of f of z equals 0. Remember, that was one of the definitions, one of the alternative definitions for a removable singularity. But I've shown how to do that technique a little already, so instead let me use one of the other alternative definitions, which said that z0 is a singularity if you can make your function continuous at z0 by defining f of z0 in a suitable way. That was another alternative definition for removable singularity, which I spoke about in the previous video. So in other words, if I evaluate limit as z approaches negative 1 of f of z, and I am able to compute this limit and it comes out to be a finite number, I can just define this to be f of negative 1, and then negative 1 will be a removable singularity. So let's see if this works. If I evaluate this limit, I get limit as z approaches negative 1 of, now I'm going to split the function f up, so I'm going to write it as e to the power of 1 on z squared minus 9 z plus 2 cubed times the limit as z approaches negative 1 of e to the power of 1 on z. Whoops, actually, what am I doing? It's not what I want at all. I want sine squared z plus 1 here on z plus 1. So as you can see, I've split it up. Now on the left is well defined at negative 1, so if I just plug it in, that limit is going to be e to the negative 1 on negative 8. Now this guy here, if I apply L'Hopital's rule, then this is going to equal limit as z approaches negative 1 of 2 sine z plus 1 times cos of z plus 1 over 1. And if I plug in negative 1 into this, I get 0. So in fact, this entire limit as z goes to negative 1 is equal to 0. So therefore, if we define f of negative 1 to be 0, then we have limit as z approaches negative 1 of f of z equals f of negative 1, right? Because I know that limit is 0. And as you know, this is the formal definition for saying f is continuous at negative 1. So what have I done? I've shown that if I define f of negative 1 to be 0, I can make f continuous at negative 1. In other words, I can get rid of that singularity. That singularity is removable. Therefore, z equals negative 1 is a removable singularity. So that's another way you can show a function has a removable singularity, to show that you can make it continuous at the singularity by defining your function in an appropriate way. Yeah, so that's for z equals negative 1. What about z equals 0? Okay, is it removable? Is it a pole? Or is it essential? Let's have a check if it's removable. Right. So if it's removable, then I should be able to do the same trick. I should be able to define f of 0 in such a way that f becomes continuous. So if I calculate this limit, let's see if I get some finite or non-infinite number. Okay, this is going to become limit as z, so this is to check z equals 0. So this becomes limit as z approaches 0. Again, I'll split up the function. And multiply by the limit as z approaches 0 of e to the 1 on z. Okay? Fairly easy to see that when you plug in the limit here, this part's going to equal sine squared 1 on 9 minus 9 times 8, so negative 72. What about this limit here? Okay, this limit actually doesn't exist. Why is that the case? So let me explain. If I can rewrite that limit. Remember, z is a complex number. It's x plus I y for some x, some y. So this is the same as saying limit as x, y approaches 0, 0 of e to the power of 1 over x plus y. Now remember, if the limit exists, then it should not matter from what direction I approach the origin. I should always get the same limit. But notice that if I approach the origin along the positive x-axis, right? In that case, y is equal to 0, and I'm approaching 0, and x is approaching 0 from the positive side. So this becomes e to the 1 on x, alright? So this is going to act like e to the infinity, which becomes infinity. But if I approach the origin along the negative x-axis, and again, because I'm going along the negative x-axis, y is equal to 0, so this becomes 1 on x, but now x is approaching 0 from the left. And as I approach 0 from the left, 1 on x is going to be like negative infinity. And e to the power of that is going to go towards 0. So as you can see, I get different limits when I approach the origin from different directions. So this limit doesn't exist. What does that mean? It means we cannot define f of naught in a way to make f continuous at z equals 0. Right? If I could, that limit would have returned some number. And that's, so equivalently, f is not removable. Sorry, z equals 0 is not a removable singularity. So it either must be a pole or it must be essential. Now remember, one of the equivalent definitions for essential for a pole was that if z equals z naught is a pole, that's the same as saying limit as z approaches z naught of the modulus of f of z is equal to infinity. Right? That's an equivalent definition. But here you can see that's clearly not the case, right? If I take the limit as z approaches 0 of the modulus of f of z, I showed in the previous when I was doing the part about the removable singularity, I showed that this limit doesn't even exist. So because it doesn't exist, it doesn't equal infinity either. I mean, I get a limit of 0 actually when I approach the origin along the negative x-axis. So because this is not equal to infinity, z equals 0 is not a pole. Therefore, z equals 0 is an essential singularity. That's one way you could show that z equals 0 is an essential singularity for this question. I guess another way you could do this, I could have written f of z as e to the 1 on z g of z, where g of z is this function here. And I could have said, well, g of z is analytic at z equals 0. I can see that. And it's going to be analytic in some neighborhood of z equals 0. So by Taylor's theorem, I can write g of z as, some sum an z to the n, right? E to the 1 on z, I think we actually looked at this in a previous video. When you do this one, you get a series full of negative powers. So you get infinite terms in principal part. Right? Whereas this guy obviously has 0 terms in principal part. Right? But when you multiply them together, when you take those two series and you multiply them together, you're still going to get an infinite number of terms in the principal part. So that's another way you could see it's an essential singularity. Either way, that's pretty much it. So I think that's as hard as these sorts of questions can get when it comes to classifying singularities. So as you can see, it's not really that difficult. It's just a matter of knowing your definitions and knowing your results, and you should be set.